Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to show or demonstrate how to find relative velocity and relative acceleration. So in this example, right, this is supposed to represent an automobile or something like that, traveling to the right here at 20 meters per second and accelerating at 3 meters per second squared. I'm going to go ahead and give this a name. I'm going to call this car A here. And then here's car B. And car B is traveling along this curved path here with a 50-meter radius. Car B is traveling at 15 meters per second, and car B has a tangential acceleration of 2 meters per second squared. So what we're going to try to calculate now is the acceleration of car B with respect to car A. So acceleration of B with respect to A. What does that look like? Alright, so the first thing we do is let's talk a little bit about vectors and how they're related. If I were to draw position vectors here, this would be the position vector A. This is position vector B. And then this vector is the position of B with respect to A. Now when I look at that picture, it's important to know that the resultant of that those three vectors is RB. So RB is equal to the vector sum of position A and position B with respect to A. So I'm going to get rid of these vectors here because I've got lots more to draw. But I'm going to go ahead and write that out, that the position vector of B is equal to position vector of A plus position vector B with respect to A. Right? This equation can be turned into velocities just by simple differentiation. So velocity of B is going to equal velocity of A plus velocity B with respect to A. And I can also write another one for accelerations. Acceleration of B is going to equal acceleration of A plus acceleration of B with respect to A. So this is what I'm trying to find, the acceleration of B with respect to A. You'll notice it's equal to acceleration of B minus acceleration of A. So I'm going to go ahead and write that down up here. Acceleration of B with respect to A is equal to acceleration of B minus acceleration of A. So now what we have to do is we have to find these things, acceleration of B and acceleration of A. And I'll start with the easy one, car A. So car A, kind of clean my picture up here. Car A is accelerating in the direction shown. That's actually a tangential acceleration at 3 meters per second squared. So the acceleration of car A, if I wrote that as a vector, is 3I. If I use this as an x-axis and this as a y-axis. And I'm going to put a little NCU for note consistent units. So acceleration of A, no problem at all. Okay, looking at car B, there's a little more going on. Car B has an acceleration that's tangential, parallel to the velocity. I'm going to go ahead and draw that. So there is a vector to represent the tangential acceleration vector, parallel to the velocity vector. Again, it doesn't even make sense to compare the length of the velocity vector to the length of the acceleration vector because they're different units. Car B is also undergoing circular motion. So there's going to be a centripetal acceleration, which is going to be towards the center of curvature. And that we're going to have to calculate. That's equal to v squared over r. And I'm going to take a moment here and calculate that. Oops, got to turn my calculator on first. All right, and I get 4.5 meters per second squared for the centripetal acceleration. So car B has a tangential acceleration of 2 and a centripetal acceleration of 4.5. Its net acceleration is the sum of the two, but it's important to note it is a vector sum, right? That net acceleration is not 6.5 meters per second squared. So we got to think of these in terms of components here. So I'm going to go ahead and draw some geometry here. If I draw a horizontal line here, it's important to note this is a 30-degree angle. That makes that one 30 degrees. 30-degree angle. I'm going to just do that and point to it. And this one right here would be 60 degrees. Okay. So the acceleration vector of B, I got to get my hand out of the way and look at this. Right. Let's talk x components first. this guy's x component is 4.5 cosine 30, and it's left. This guy's x component is 2 cosine 60, again left. So the x component of the acceleration vector for B, let's see, is going to be minus 4.5 cosine 30 minus 2 cosine 60 I. And again, I'm going to point here, note consistent units. I'm going to leave them off just to shorten my writing up. All right, now let's talk about the y component of the acceleration of car B. All right, so this tangential acceleration vector, its y component is here opposite the 60. So we're going to have 2 sine 60 for that piece. All right, the centripetal acceleration vector is here. Its y component would be here pointing down. It's opposite the 30-degree angle. So we're going to have minus 4.5 sine 30, right? J. So there's the acceleration vector for car B. All right, so the acceleration of B with respect to A is going to be, we need to take acceleration B minus acceleration A. And again, that's a vector equation, so that has to be done vectorially. So that's going to be this guy minus this guy. So I guess I'll go ahead and write that all out. So we're going to have minus 4.5 cosine 30 minus 2 cosine 60. So that's this minus 3 I. Then we're going to have plus. All right, j direction, we're going to have this guy, 2 sine 60 minus 4.5 sine 30, right, minus the j component of this, but it doesn't have one, so I'll just put minus 0. And then I'll just tack that on j. And now what we do is we just got to go through and calculate a value here. So I'm going to go ahead and just pause this just for a moment here while I do that. Okay, I'm back. So I calculated values. I ran that and I got negative 7.9. I ran that and I got negative 0.5. I'm going to go ahead and attach units to it. These are in units of meter per second squared. So there's the acceleration of B with respect to A. You know, big points, you have to come up with the original equation for it. I usually like to draw my position vectors first and write out the position relationship for for the two particles, in this case A and B. Differentiate it, gives you an equation for velocity. Differentiate it again, gives you the relationship there for acceleration. Then it just boils down to finding vectors for the acceleration of each particle. Sometimes, like in this example, that's pretty well no problem at all. That's a nice one-dimensional acceleration, no centripetal or Coriolis terms or anything like that, so just 3 meters per second squared to the right. However, sometimes they're a little bit more complex. You have to recognize, okay, this guy right here has a tangential and a centripetal. And in this case, the centripetal had to be calculated. And then the next step is we have to break the vectors down into components and write the acceleration vector in unit vector form. That's a nice, easy way to take the difference between those vectors, acceleration of B minus acceleration of A. So, hope this video demonstrates pretty well how to do that. Have a great day.